All right, everyone, welcome back to Calculus 2. So normally what I do when I miss a day of class is I just record whatever I was going to do in class that day, put it as video and ask you guys to watch it. But as I said earlier in the class, we're learning these series tests in ascending order of importance. So the integral test was like mostly just a stepping stone to get to the p-test, which is kind of useful. And then we learned about the alternating series and we learned about comparison tests. So that means, and today is going to be our last day of learning about new tests. And based on what I said, that means that today is going to be our most important tests to learn. And the reason why they're going to be so important is because we're going to be using them all the time for these infinitely long polynomials that we have coming up. So today I want to just give this lesson live so you guys can have questions and everything. And then what I'm going to do is I'm going to record what was originally going to be Friday's lesson here. And Friday's lesson, like what we were originally going to do today, was just do a bunch of practice, seeing if series and sequences, or sorry, seeing if just series converge and stuff like that. So I'll make a video where I do a bunch of that. And if you guys have any questions on that on Monday, I'll feel free to ask them. All right, so let's go ahead and get started here. So today is lesson, oh, that pen doesn't work. That's right. Today is lesson 22. Oops. There we go. And it's going to be the root and ratio tests. Okay. So the ratio test in particular is going to be our go-to series test. 90% of the time, we're going to use a series test in the future. It's going to be the ratio test. Or it might be like a super obvious test for divergence or stuff like that. But most of the time we need to do any test that takes any amount of work, it'll be a ratio test here. When will the lecture recordings get uploaded? I'll upload the alternating series one right after class. I'm sorry I forgot to do that earlier. And I'll upload the, oh, the mic's not working again? Oh boy, after the rocky start. All right, is that better? Better? Okay, good. All right, anyways, yeah, and then I'll upload, I'm gonna make the video for what we were originally gonna do today. I'm gonna make that tomorrow. So you guys should be able to see that then. All right, so let me continue talking about these. So why are these tests so important? Let me first talk about the ratio test. What is that? Well, the first nice thing about the ratio test is that there aren't any conditions on the sequence you're adding up in order to do this. So you could use the ratio test on any series you want. Doesn't mean it's necessarily a good idea to use it on a series, but there's no kind of conditions like, oh, AN needs to be positive, AN needs to be continuous or decreasing or anything like that. There's no conditions you need to check beforehand. There's no conditions. So what is the test? Suppose we have a series A, which is the sum from n equals 0 to infinity of A sub n. What we do is we compute the limit L, which is the limit as n goes to infinity of the absolute value of AN plus 1 over AN. So what we do is we take the terms in our list that we're adding up and we pretty much put the next term divided by the previous term here. And we send that limit as n goes to infinity. Now, based on what this is, if L is, and then there are going to be three different instances here. So if we have L being greater than or equal to 0, but then strictly less than 1, then A converges, and it doesn't just converge, it actually converges absolutely. So remember the distinction with converging absolutely here is that it doesn't even, if it had an alternator, it didn't need it to converge. It's going to 0 so quickly that it doesn't matter if it has an alternator or not. Okay, so that's what happens. So we get converges if it's between 0 and 1, including 0, but not 1. If L is greater than 1, then the series A diverges. Now, the one downside of the ratio test is if we get L exactly equal to 1, then the ratio test is inconclusive. We need to use a different test instead. So another test that was inconclusive in the past here was the second derivative test way back in Calc 1. So remember, if we had a second derivative of 0 for that, it could be a min or max or neither. We would need to use a different test to check. So it's kind of the same thing here. If we get L is 1 on the nose, we don't really know for sure what's going to happen. So we need to use a different test. All right, now why does this work? Why does this limit tell us so much about the series here? Well, effectively what this is it's comparing our series to a geometric series. So let's say, for example, we have the sum from n equals 0 to infinity of 1/2 to the n, right? So a sub n plus 1, I replace all of the n's with n plus 1s, would be this. A sub n would be 1/2 to the n. So if I look at my limit of an plus 1 over an, what's that going to give me? Well, I don't need absolute values because everything here is going to be positive right here. I have 1/2 to the n plus 1 divided by 1/2 to the n. And then that and this will cancel out because I have one more 1/2 up here than I did down here. So we end up getting 1/2. Now, what is this saying? It's saying that if I keep dividing successive terms by each other, each new term is going to be about 1/2 the size of the previous term, or actually exactly in this case. And if we got, say, like 3/4 from this, this is going to be roughly 3/4 the size of the previous term. So if we get something less than 1, that means the new terms are going to be smaller than the older terms. So that means our series is decreasing and it's going to converge. But on the other hand, let's say we ended up getting something like 2 from this. That means our new terms are always about twice the size of the old ones. And that's definitely bad here because then that means our terms are literally or almost doubling in size every time. So what we're doing is we're effectively treating this like a geometric series. We're looking at the multiple of the new terms based on the old ones here. What's in the denominator? This was 1/2 to the n. So we have a sub n is 1/2 to the n. A sub n plus 1 is 1/2 to the n plus 1. So I have one higher power here than I did down there. So this simplified to be 1/2. All right, so let's go ahead and actually use this on a series that isn't just a geometric series. Okay, let's use the ratio test on this series. The sum from 0 to infinity of 2 to the n over n factorial right here. Okay, now we know from earlier, at least based on what I said, that factorials are higher on the hierarchy of functions than exponential functions are. So it seems pretty likely that this is going to converge. But we don't know for sure. Just being higher in the hierarchy of functions does not guarantee that this is going to converge. So we need to use a test. So let's use the ratio test here. So in order to use the ratio test, we don't need to do any conditions. We can use the ratio test on anything we want. We just need to compute this limit. So we have the limit as n goes to infinity of a sub n plus 1 over a sub n. Okay, now what is that in this particular instance? Well, let's see here. If I plug in n plus 1s for these, I have 2 to the n plus 1 over n plus 1 factorial. And then I divide by 2 to the n over n factorial. Is this the absolute value of the sequence? Yes, we do need the absolute values. Now, it's really easy to forget about them because a lot of the series that we'll be looking at do end up being positive, but we're really going to need them for the lessons that come after this. So don't forget about these. But in this example, everything is positive, so we can't get rid of them. Now, if I simplify this fraction, dividing by a fraction is the same as multiplying by its reciprocal. So I'm effectively looking at this right here. Now, the fun part about doing the ratio test is if you kind of feel satisfying, like satisfied simplifying things or canceling stuff out, you're really going to like this because there's essentially just a ton of canceling with this. So for example, we have 2 to the n plus 1 up here, and we have 2 to the n down there. What's going to happen when we simplify these? What are we going to get from that? That's right. We're just going to end up getting 2 right here. Because we have 1 power higher up here than we did down there. Okay, now let's think about the factorials right here. So this is going to be a little different. Remember what factorials are. A factorial starts at whatever number has the exclamation point next to it, and you keep multiplying down by successive numbers. Oh, it looks like you guys already kind of figured this out, but let's see why that is. So n plus 1 factorial is n plus 1 times n minus 1, n minus 2, and then 3 times 2 times 1. N factorial is the same thing, only it just starts at n instead. So if we have these canceling out, one's on the top, one's on the bottom, we're just going to be left with an n plus 1 where the n plus 1 factorial was, because they share all of the other terms. So when the dust settles with our cancellation here, we end up with 2 divided by n plus 1. So this is going to be our limit here. All right, now let me ask you guys this. What is this limit going to end up equaling? It's going to be 0. That's right. Last I checked, 0 is indeed less than 1. So since we got a result that's less than 1, we see that our original series is going to converge absolutely. So we say that this converges by the ratio test. All right, and that's it. That's how we use the ratio test. Now, let me explain what the ratio test, what types of series it's good for. The ratio test works especially well if you have a factorial. If you have a factorial in your series and you need to do a series test on it, immediately do the ratio test. That's almost certainly the best one to use. Ratio test also works well with exponential functions or other high-powered functions like n to the n or things like that. However, if you don't see any, well, actually, let me save that for later. I have a specific example that's going to talk about that. Why don't you guys give this a try? Have some fun canceling here. Let's see here. Practice 1. Let's go ahead and use the ratio test on this series. The sum from 0 to infinity of n plus 4 factorial divided by 4 factorial, n factorial, and 4 to the n. So why don't we go ahead and use the ratio test here? Why don't you give this guy, I probably say literally exactly the same thing every time. I just get into a rut. Yeah, give this a try. Yeah, it's almost shouting at you with all the factorials. The n plus 4 on the top become n plus 5? Yeah, that's right. So anytime you see an n and you're doing an plus 1, just replace every n you see with an n plus 1. Don't worry, Amber, we'll go over it in a minute. Once you get used to it, the ratio test is definitely one of the easier ones to use. Do you not change the 4 factorial because there is no n? That's absolutely right. With those, write out what the factorial is. Kind of like how we wrote out what these factorials are. Why don't you guys try writing out what n plus 5 factorial is and n plus 4 factorial is? And then I think you'll see how it works. I got an answer, 1/4. I guess that'd be fitting with all the 4s. All right, give you guys another minute here. I wonder if a number with a question mark means anything. I never looked that up. Later on in the class, we're going to see what it means to have 2 exclamation points. And it actually means something different. Oh, did you already see that on the homework? Oh, yeah, that's right. I gave that. Yeah. Yeah, there it is. All right, let's go ahead and take a look at this guy. Let's see. All right. So let's try the ratio test with this. So we have the limit as n goes to infinity of the absolute value of an plus 1 over an. All right. Now, most of the time when we use the ratio test, we're going to have a fraction. So I'm just going to go ahead and skip to the step where we have this with n plus 1s in place of all the n's times the reciprocal of the original. So if we do this, it's the same thing as the limit as n goes to infinity of absolute value. Let's see, I have n plus 1 plus 4, so that's n plus 5. And then I have 4 factorial, n plus 1 factorial, 4 to the n plus 1. And notice that I didn't change anything with that 4 factorial. There's no n's there, so we don't need to do anything with that. And then I multiply by the reciprocal of the original because I'm dividing by the original fraction. So I multiply by the reciprocal of the original one here. Okay, let's move over to get some space here. Now let's see here. We can get rid of the absolute values because there's nothing that could be negative here. One nice thing happens is that the 4 factorial and the 4 factorial just cancel out. So any constants that we have that are included, and this is a constant, it's just 24, those will just cancel out in the ratio test. Let's see here. We have 4 to the n and then a 4 to the n plus 1 here. So we saw how exponentials cancel out. We have one copy of the higher power, and that's going to be in our denominator. So we're going to have a 4. We already saw how n factorial and n plus 1 factorial canceled in the previous problem. If we have an n factorial and an n plus 1 factorial, the n factorial entirely goes away, and we're just left with an n plus 1. Okay, so we got that. Now all that's left to do is do n plus 5 factorial divided by n plus 4 factorial. And let's see how that will work. So n plus 5 factorial, it starts at the number n plus 5, right? We always start at the number that's next to the exclamation point. Then we start going down by one number. So what's one number lower than n plus 5? It's going to be n plus 4. And then what's one number lower than that? It's n plus 3, n plus 2. And we keep descending through the numbers, just like before, until we get to 3 times 2 times 1. Now with n plus 4 factorial, the situation is the same, only we start at n plus 4 instead. And then we have n plus 3, n plus 2, 3 times 2 times 1. So if we have this in the numerator and then this in the denominator, all of these will cancel. And we're just going to be left with an n plus 5. Right there. All right, so then we've canceled these out. And I think that's everything from the original. So now we're just looking at the limit as n goes to infinity of n plus 5 over 4 times n plus 1. Now remember, the way to do, what was I saying? The way to do the limit of a rational function as n goes to infinity is we check the degrees. So the degrees for this are the same. All right, and then we look at the ratio of the leading coefficients. So we have 1 times n over 4 times n. So that'll end up giving us 1/4 here. That's also less than 1. So this converges by the ratio test. All right, so there we go. There's that example. All right, let's do maybe 1 or 2 more with the ratio test, and then I'm going to talk about the other test we're going to learn about today called the root test, which is very similar. All right. Example 2. Let's take a look at this. We have the sum from n equals 1 to infinity of negative 2 to the n, 2n factorial, and then we have n to the n down there. All right. So let's see here. Let's go ahead and do our ratio test. So I'm going to put in negative 2 to the n plus 1. Now, this is where things get a little bit confusing. The plus 1 for the n goes exactly where the n is. So since this n was multiplied by a 2, the n plus 1 will be multiplied by a 2. And then we have n plus 1 raised to the n plus 1. And then we multiply by the reciprocal of the original right here. All right. So let's see here. How are we going to cancel this out? Well, we have the usual exponentials here. We have negative 2 to the n plus 1 over negative 2 to the n. That will just simplify to be negative 2. And that's the only thing that could potentially be negative here. So I'm just going to get rid of the absolute values, but then write that as a 2. All right, so we saw what happened with that. Now the rest of this is going to be a little bit more complicated. If I distribute this 2 right here, I actually get 2n plus 2 factorial. So you may have expected that to be 2n plus 1 factorial, but remember the n plus 1 goes directly next to that 2. So we're going to end up with 2n plus 2 factorial when we multiply. Now, what's 2n plus 2 factorial divided by 2n factorial? Well, let's write it out to see. 2n plus 2 factorial is 2n plus 1, or sorry, 2n plus 2 times 2n plus 1 times 2n minus 1 And we keep going all the way down. And then meanwhile, 2n factorial starts at 2n, and then it starts going down. So if we cancel all of this out here, we actually end up with 2 terms left over on the top. So we have 2n plus 2 and 2n plus 1. That's kind of the surprising thing that happens with this right here. All right. So now what we have left over is this n to the n and then n plus 1 to the n plus 1. So we'll deal with that in a second. All right. So we've simplified this a little bit. What I'm going to do now, I see I could pull a 2 out of this. So I factor a 2 out of here, and then I have 4. And then I have n plus 1, 2n plus 1, n to the n over n plus 1 to the n plus 1. All right, now this part's going to get a little tricky with the algebra here. So we have n plus 1 raised to the n plus 1 power down here, right? But we also have an n plus 1 raised technically to the first power up here. So since those exponentials have the same base, I can combine them together. And this has the bigger exponent, so I subtract 1 from n plus 1. And I get 4 times 2n plus 1, n to the n. And then what's going to be my denominator now, if I simplify? Not just n plus 1. Yeah, it's going to be n plus 1 to the n. That's right. Because we had one of these n plus 1s up here, and we have n plus 1 of them down here. So we subtracted that exponent, and now we have n right here. All right, let's write this over here so we have a little more room. Okay, now let's see here. Now that we've done that little thing, we have n to the n over n plus 1 to the n. So since they have the same power, we can combine them into the same fraction like that. All right, now what I'm going to do is I'm going to focus on this guy right here because this one's kind of weird. I'm going to see what's happening with this, and then I'll deal with like whatever comes out of this, I'll combine it with that and then finish off the limit. So I'm really focusing on this right here. Now, one thing I can do to make this look a little bit different is I can add and subtract 1 on the top. And you'll see why I'm going to do that in a second. So I have n plus 1 minus 1 over n plus 1 to the n. Okay, now why did I do that? Well, I have n plus 1 over n plus 1. That's going to end up being 1. But then I have this negative 1 over n plus 1. Okay, so this is what I was able to turn this into here. Okay, now does anyone kind of, like, let's take a look at this guy. Does anyone think this kind of looks familiar? Maybe not exactly the same as something we've seen before, but kind of similar. Yeah, so this kind of looks like E. That's right. It looks kind of similar to what E is. There's a few differences, though. There's a minus sign here instead of a plus, and then there's a plus 1 down there as well. But you are right. This does have something to do with E. So let me give you the relationship between this and E. Here's just kind of a fact that we should use. The limit as n goes to infinity of 1 plus a over n plus b, where these are constants, to the n is going to be e raised to the a power right here. All right, so that's going to be useful here because in our case, a is negative 1 and b is 1. And actually notice it doesn't matter what b is in the outcome here. This could have been n plus 100 down there or something like that, and it still would have ended up being e raised to the negative 1. So based on this formula here, this limit, this part of the limit is going to be e to the negative 1. And if you want to see where this comes from, you could prove this using L'Hopital's rule if you want. So this whole part of the limit will go to 1 over e, or e to the negative 1. Okay, well, so that's what we got out of this limit. Now let's combine it with the rest here. So we have 4 over e times 2n plus 1. Okay, and then what's the limit as n goes to infinity of this going to be? It's going to be infinity. That's right. Yeah, because there's no denominator, or at least no denominator going to infinity anymore. So there's just positive infinity. And that's greater than 1 for sure. So we did all this work to see that this series is just going to diverge. Two n factorial and then diverges by ratio test. Euler. If you want to make a mathematician really mad, that's like probably one of the fastest ways to do it is pronounce his name like that. I don't really care that much, but a lot of people are very picky about that pronunciation. All right, so this one we kind of pull out all the stops for the ratio test. This is like pretty much as bad as the ratio test can get. So we saw back here, let's recap. We saw what happened with this. We need to distribute to the n plus 1 over here. We ended up getting 2 terms from that. We factored out and we had to cancel with this weird n plus 1 to the n plus 1. And then we had to make this look like the limit for e right here. So the limit for e shows up quite a bit. So I would definitely remember this limit right here. That's going to be very helpful. It's better than doing L'Hopital's rule every time you see it. That would definitely take way longer. But yeah, this one's a ratio test where we had to pull out all the stops to do it. All right, now I want to do one more quick example of the ratio test, and then we'll get to the root test here. Let's do a very simple one to kind of cool down from this very tough one here. Let's use the ratio test on the sum from n equals 1 to infinity of 1 over n. Okay, now actually this is kind of a stupid question, right? Because we already know what the answer to this is. What's the answer to this question? Is this going to converge or diverge? It's going to diverge, right? We already know that this diverges by the p-test. Okay, well, that means that if we put this in the ratio test, it's probably going to say the same thing. So let's just go ahead and do it. So we have the limit as n goes to infinity of the absolute value. Let's see, an plus 1 would be 1 over n plus 1. We multiply by the reciprocal of the original. This time there's no canceling out, although we can get rid of the absolute values. We just have the limit of n over n plus 1 as n goes to infinity. And this is going to equal 1. Okay, now what is the significance of 1 for the ratio test? You guys remember that? Right, it's inconclusive, meaning that the ratio test can't tell if this is going to converge or diverge. And that seems kind of pathetic, right? Because this is one of the easiest series to look at and know whether it's going to converge or diverge. It's probably one of the first ones we learned about here. But the ratio test can't tell us if we're going to have a convergent or divergent series. So this is inconclusive by the ratio test. Okay, so that kind of begs the question, what if I maybe do a problem like this, and then I get down to something that's just 1? Wouldn't that be kind of annoying? Yeah, that wouldn't be so great. So how do we know in advance if the ratio test is going to give us something that's inconclusive? And usually, at least 90% of the time when we get something inconclusive from the ratio test, there are no functions of exponential power or greater. One thing in common with all of the examples before this is that they all had an exponential function or stronger involved. The very first example we did today had a 2 to the n in it. This example had a whole host of things that were exponential or stronger, like 4 to the n, n factorial, n plus 4 factorial. This had a super exponential where even the base is a variable as well, and it had a factorial. All of those had exponential power or higher. So the ratio test will say something interesting about that. But if you have only polynomials, or you have only logs, or weaker than exponential functions, it's going to give you 1. So you shouldn't use the ratio test if you don't have any functions of exponential power or greater. If you only have polynomials or you only have logs, it's going to be a waste of time to use the ratio test. Why can't we use the E limit identity on n over n plus 1? This is because we're not raising anything to the n here. So if we were raising this to the n, then this would be, that would end up being 1 over E in that case. All right, so the moral of the story is we can't use the ratio test all the time. We're going to get inconclusive if we don't have a powerful enough function involved. Okay, now I want to talk about the root test. So the root test is, I don't know, I like to consider the root test like the little brother of the ratio test. It kind of feels the same to use it, and it's also pretty useful, but we just don't use it quite as often. But it's something nice to kind of have in your back pocket here. Okay, so what is the root test? Okay, so suppose we have a series A. It's the sum from 0 to infinity, a sub n. Then what we do is we compute a limit, but this time the limit's going to be different. It's the limit as n goes to infinity of absolute value of a sub n to the 1 over n power right here. Okay, so we're going to compute this limit. And then based on what this limit is, if L is in between 0 and 1, including 0 but not 1, the series converges absolutely, if that's a distinction you care about. If L is greater than 1, the series diverges. And if L equals 1, the root test is inconclusive. So it's literally exactly the same criterion that we had for the ratio test. It's just going to be a different limit than before. But otherwise, this is identical to the ratio test here. Okay, so let's go ahead and see an example of this. Example 4. So let's use the root test. Oh, by the way, before I continue, I want to talk about this. The root test is almost always the same condition, or is almost always inconclusive, exactly the same time that the ratio test is. Did I say that right? The ratio and root tests are always inconclusive at the same time, meaning that if you only have polynomials or logs or weaker functions, you're just going to get 1 from the root test as well. And also, if you try the ratio test and that doesn't work, don't try the root test, because that's probably not going to give you anything other than 1 either. Are there any preconditions? No. Just like the ratio test, the root test has no conditions you need to satisfy before you start the test. All right, so let's go ahead and use the root test on the sum from n equals 1 to infinity of n plus 1 over n to the n. All right, so let's compute our limit here. We have the limit as n goes to infinity of the absolute value of n plus 1 over n to the n raised to the 1 over n. All right, well, everything in here is positive, so once again, we can get rid of that. Don't forget about these absolute values, though. These will be important in the next lesson. So we have n plus 1 over n to the n to the 1 over n. All right, let's apply the power to the top and bottom. Lots of n's floating around. Now, the nice thing about this is that we have n to the n, and then when that's raised to the 1 over n power, those are going to cancel out. So that's where the cancellation happens here. So now we're just looking at n plus 1 raised to the 1 over n, divided by n. Now let's see here. Here's a fact. I don't know if I mentioned this in class or not. I may have skipped this one over by mistake. But here's a fact that will be helpful with the root test. If you have the limit as n goes to infinity of any polynomial to the 1 over n, that's going to equal 1, no matter what polynomial it is. So it could be like n to the 1,000 or something like that. And if you send that to infinity with a 1 over n right there, that's going to give you 1. And this also works for logs too. So if you have like powers of natural log or something like that, those will also just be sent to 1 if they're inside a 1 over n power. All right, so then this is our polynomial right here. Our polynomial is n plus 1. So if we send that to infinity with a 1 over n, we're just going to end up with 1. But meanwhile, we have this n down here, which actually is going to infinity. So we end up with 0 for our test here. So all weaker functions, yeah, anything that's polynomial power or weaker is going to get sent to 1 if you put it in a 1 over n power. Now watch out, if you have like a polynomial times something with logs, or maybe logs raised to some polynomial power or something like that, that might not necessarily go to 1. But if you just have logs or polynomials on their own, yes, that will definitely go to 1 in this context. Let's see. What did you cross out on the bottom here? This was n to the n, and that was raised to the 1 over n. So remember, exponents multiply. So we have n divided by n just gives us n to the 1. So it's n right here. And how did I get to 1 over n? This guy went to 1. All right, and then we end up getting 0. So that means that this converges by the root test. All right. How do you know when to use the root test versus the ratio test? I'll be honest, I'm strongly biased towards using the ratio test. So I just kind of use that by default. If you have a factorial, I would definitely use the ratio test because factorials don't play too nicely with the 1 over n here. However, if we do have a bunch of nth powers like this, and in the next example, I would use the root test instead. So if you see a bunch of stuff raised to the n or something involving n, then I would use the root test. But if there's a factorial in there, definitely use the ratio. All right, so here's our last practice problem, and then where's our last practice problem? Oh, here it is. So we have one more practice problem, and then you guys can go enjoy your weekend. Does it matter that the n plus 1 to the 1 over n is an indeterminate form? Yeah, so it's an indeterminate form that will always end up being 1. So we could have done the e to the ln trick with L'Hopital's rule here, but I'm just telling you that that will always end up being 1 if the thing we have in here is a polynomial. So it is an indeterminate form, and if we do the limit, if we do all the work, it'll end up being 1. All right, so why don't you guys take a look at this? The sum from 1 to infinity of 2312 raised to the n squared divided by n raised to the n squared. All right, so go ahead and try the root test. Have we learned enough about to do the negative 1/12 thing yet? No, we haven't. I'll show you guys in class once we get that. Once we get there. Our power series on the exam coming up. Yeah, so today's material, and then the stuff I'm going to go over on the video is mostly a review. So essentially today's material is the last stuff that's going to be on the exam. So the stuff we're going to learn about on Monday is not going to be on the exam. It's just awkward timing. If you don't know what a power series is, don't worry about it yet. What lessons are on the exam? Whatever lesson we ended on with integrals, up to this lesson. So I think it was like 15 through 22, maybe. When is the next exam? It's next Friday. And by the way, I posted a practice exam for you guys to take a look at. And I also posted some old exam twos in the miscellaneous section of Canvas. So if you guys want to start studying, you now have resources. So 15 sequences, okay. Yeah, so we have our exam's next Friday. It's gonna be over all the series and sequence stuff we've done so far. Don't start panicking. Traditionally, this exam actually has the highest average among all of them. So if you guys are like usual semesters, you guys will probably do really good on this one. How many midterms do we have? 3, and then a final, cumulative final. We don't have Taylor series. I haven't said the word Taylor yet, so we don't have to worry about it. I just did. All right, well, now it's on the test. I'm just kidding. All right, give you guys another minute to look at this. This one's not too bad with the root test. Oh yeah, what's up? Yeah, you could take the limit of the inside of that. And if it's going to go to like 0, for instance, then the whole thing will go to 0. Your birthday's actually today. Happy birthday, Matthew. Happy early birthday. Statistically, it's probably most class days, it's at least someone's birthday in here. So we usually have what, like about 200 people? Probably say happy birthday most days and it'll work out. Not to degrade anyone's current birthday. Anyways, let's go ahead and take a look at this. So let's do the root test. So that's the limit as n goes to infinity of the absolute value of this monstrous function, 2312 to the n squared over n to the n squared. And all that's raised to the 1 over n power. Okay, these are certainly positive, so we can get rid of the absolute value here. All right. And we have the limit as n goes to infinity. Now, if I apply the 1 over n to each of these n squared powers, what will happen? Well, remember, if you have a power raised to another power, you multiply them together, right? So I'm going to have n squared times 1 over n. That will end up just being n. So when I simplify this, actually, I don't even need that anymore. It's going to end up being 2312 to the n over n to the n. But another way of writing this is 2312 over n raised to the nth power right here. All right, now let's see here. If I take the limit as n goes to infinity of this, what am I going to get? What's the limit of this going to end up being? Yeah, it's going to end up being 0. That's right. At first, you might be a little cautious, be like, this kind of smells like an indeterminate form. We have like 0, something going to infinity. But if you have a number going to 0 and you multiply that by itself a bunch of times, it's going to get even smaller and go to 0 even more quickly. So that's actually not 0 to the infinity is actually not an indeterminate form. It's just always going to be 0. So we just end up getting 0 for this limit, meaning this converges by the root test. All right. Well, that about does it for today. So as I promised, sometime tomorrow, I'll post a video giving you guys a bunch of guidance and advice and a bunch of examples on which series tests to use when. And then on Monday, we'll do a lesson that's going to be relevant to stuff after the exam. Next Wednesday, we'll review for the exam, and same thing on Friday. So I will see you guys next week.